Alexandre. Hello to everyone attending this seminar. Thank you all for your presence here. And today we have the great pleasure of having a seminar by Professor Marijke Haverkorn from Radboud University in the Netherlands. Professor Marijke, thank you a lot for accepting this invitation. Marijke, let me introduce a little bit. Professor Marijke, she got her PhD in astronomy at Leiden University. She worked as a researcher in several institutes around the world, including Harvard University, University of California, and the Netherlands Institute of Radio Astronomy. And since 2011, she's professor at the Institute of Mathematics, Astrophysics, and Particle Physics at the Radboud University in the Netherlands. And there she leads her group. The name of the group is Galactic Ecosystem Group, and her research interests are mainly galactic magnetism and its interaction with the interstellar medium, interstellar turbulence, and the radio and optical polarimetry. And today, Professor Marijke is going to present the seminar, The Magnetic Fields of the Milky Way. The questions can be done to Marijke after her presentation. If you are following the seminar on the YouTube channel, you can just type your question in the chat. If you are in Google Meet, you just push the button, raise the hand at the end of the seminar. And before the seminar starts, I would like to ask everyone to turn off microphones and cameras. And now, Professor Marijke, you can start it whenever you are prepared.
Okay, thank you very much, Reynaldo, for the introduction. And thank you both, Reynaldo and Maria Victoria, for the invitation to give this presentation here for you today. Let me start the presentation. I'm assuming that you'll see it, that you're seeing it in the right way.
Yes.
Okay, thank you. So magnetic fields in the Milky Way is an old love of mine. And I started out as a radio astronomer, and now more and more get pulled into optical polarimetry, which is what landed me this collaboration with your colleagues in Sao Paulo, amongst others. So I'd like to start out with thanking my collaborators. Here there's a whole list. These are the top few lines are my students and postdocs, some of them former, that are or were in my group, and whose results I'll be presenting mostly. And then the second group of collaborators, Antonio Mario and Claudia and Reynaldo in Brazil, and a colleague in Japan on work with me on the starlight polarization. And there's a group in Croatia, in Zagreb, people who are experts in radio polarimetry who I work with, and then Imagine that I'll get back to. So when I started out, this is now more than 20 years ago, doing a PhD on weird radio polarimetric filaments that we thought had something to do with galactic magnetic fields. Then I had the feeling that galactic magnetic fields were really something of a niche. I guess cosmic magnetic fields in general, also extragalactic cluster magnetic fields. It was a little bit of a niche science. And back then it was still a little bit true that if you would have some unexplained phenomenon, then you could always say, well, that's probably magnetic fields, or it's probably turbulence. And in these 20 years, I saw the field grow and grow because of more technological possibilities, numerical possibilities. And so now I think it's a very mature, or I guess again, a very mature field of science with many different telescopes having key science projects around galactic or cosmic magnetism. And so now we see many more diverse results. And some of them are, for instance, images as beautiful as this. This is obviously not the Milky Way, but this is an edge-on external galaxy. This is from the Changes survey. And the blue stripes you see are synchrotron emission. Yep.
Marijke, sorry.
Yep.
We are still in the cover of your presentation. Maybe it would be necessary to stop sharing and start again. Maybe some problem happened.
Sorry, you don't see the next slide?
Now we see.
Oh, you do. Okay, sorry. Yep. Okay, so you do see this, my synchrotron filaments in the adjunct galaxy now, I hope.
Yes.
Actually, they're not mine. They're from the Changes survey. But you see these beautiful filaments. And the blue is the intensity of synchrotron radiation, being proportional to magnetic field strength, more or less. And the lines that you see are a visualization of the magnetic field orientation. So you see on the one hand that this magnetic field is fairly coherent, right? It has coherent structure basically over the scale of the whole galaxy, but it also has many complexities and small-scale structure in there. And of course, this complexity and small-scale structure, it becomes more and more, the better you look, right? And the more detailed you look. And so there's no better galaxy than the Milky Way to see all this complexity in its glory. And this is a very small part of the Milky Way. What you see here is a dust emission a polarized dust emission from the Planck satellite in color. And again, these lines are a visualization of magnetic field orientation. And again, there's some of this very coherent structure here. This is along the galactic plane, but also it's very clear here that there are small-scale structures everywhere. And these are interacting with, in this case, with the Polaris flare molecular cloud. And so there's this turbulent component, and there's a component in the that interacts with discrete objects, with clouds, with supernova remnants, and then the coherent field. And this is also what you see from simulations. These are very nice. This is a very nice image of a simulation by Kim and Ostreicher, where you see the galactic plane here in the middle, and you see a gas density, gas temperature, and here on the right, this is magnetic field strength. And again, the complexity is really mind-blowing, and this is so many turbulent, small-scale turbulent structures. And so the magnetic field, one of the important aspects of it is that the energy density of the field here is approximately equal to the energy density in turbulent gas, is approximately equal to the energy density in cosmic rays, which means that these three components are in constant interaction. So it's not, the magnetic field is not just a passive tracer, but it does give feedback on the gas. And that makes it so complex, but it also makes it so interesting. Here are a few examples of this role of the magnetic field. For instance, here in gas clouds, this is a neutral hydrogen cloud, the Regal-Quecher cloud. It's a fairly nearby cloud in the galactic plane. You see these long, very narrow filaments. And if you overlay magnetic field orientation, as gotten from starlight polarization, you see that indeed these filaments do follow magnetic field lines. So gas dynamics is one aspect that is very much shaped by these magnetic fields. And the second one is star formation. These fields influence star formation. There's still a lot of discussion of how exactly and when and what exactly. But it can, basically, there are two ways. On the left-hand side, you see an artist's impression of a star that is being formed. And you see that the magnetic field lines, these yellow lines in that star, are connected to this accretion disk, and in that way they're breaking the star's rotation. So they carry away angular momentum from the star, enabling heavier stars or more massive stars to form. And on the right-hand side, you see actually an effect of the opposite effect of magnetic fields and star formation. That, for instance, in these dark cores, these molecular cores where stars might form, there's a magnetic field threading them, and you see something like an hourglass shape in this magnetic field. That if the cloud tries to contract even more, the magnetic fields are, they're mostly frozen in, they're resisting, and so you get an increased magnetic tension that tries to work against this collapse of the cloud and the star formation. So there's a very complex but significant interaction between the two. And then the last example I want to give is that of cosmic rays. So cosmic rays are charged. They obviously are deflected by magnetic fields. And here is a visualization of a model where these grayish lines are magnetic field lines in the Milky Way galaxy. So a lot of them are in the plane of the galaxy, but you also see vertical magnetic fields. And here these thick white-ish lines are trajectories of different ultra-high energy cosmic rays that come, that all eventually end up at Earth, here, the simulated Earth, but they come from very different directions from the arrival directions that we see. So if we ever want to be able to trace back those cosmic rays to their real origins, we need to have a good enough handle of these galactic magnetic fields to be able to correct for them. And so this is one of the main challenges that I'd like to discuss today, is how can we construct a model of the galactic magnetic field. And I don't mean a full-fledged MHD simulation, but something like a heuristic, a parametrization of magnetic field with best fit parameters that we can use as something of a standard model to, for instance, to correct cosmic ray trajectories and to use in analysis of Milky Way dynamics and the interstellar medium. And so these models like that have been constructed in the last, I think, 10 years or so, well, and further, but there were a number of them the last 10 years. And here you see an example of the top view of coherent components here, and here's the side view of this coherent component. And the bottom shows you how the random component is modeled, and for three different models, for what they call the Soon model, the Jensen and Farrar model in the middle, and then there's a Jeffy model in the right-hand side. Another thing with these models is that they all, as you can see here, right, they all are different in the sense that they have different parameters, different ways of parametrizing things, and different ways of treating the random component, but they also they fit to different sets of data, so to different observables. And this makes it very different to really quantitatively compare these models. These models are all, as you can see, they're very, very simplified, so none of them have chi-squareds close to 1, well, depending on what kind of errors you use. But these models are all far from perfect, and it's very hard to say, because they're so heterogeneous, which one is better than the other one. And this is very important to do because, well, if I can come back to this example of ultra-high energy cosmic rays, here's a nice illustration of how important this modeling is. That here, this is a picture that made by Glennis Farrar. If you would have an ultra-high energy cosmic ray, a proton, that would arrive from this part here in the sky, and you would calculate what the deflection would be from the magnetic field in the Milky Way based on different models, then all these little arrows give the deflections according to different models. So they're not even close to each other, right? They all predict, or most of them predict, something completely different. And the thing is that at the moment we cannot say which of these arrows is more likely, which of these deflections is really the one that we should use. And the right-hand figure gives you actually more or less the same image, then for two different models, blue and the red models, and across the whole sky, you see that these deflections differ a lot across the sky. They also differ a lot from model to model. And so with a bunch of people, we started a couple of years ago to try to think about how we could improve this and how we could make these models more comparable. And what we came up with is what we call IMAGINE, is the Interstellar Magnetic Field Inference Engine. So this is a software suite, it's a Bayesian inference machine, and the big part, or the extended version of it is shown here. But basically what it comes down to is this, is that we do have a Bayesian software that samples through different parameters of a magnetic field model that we put in, and we want to compare that to data to find the right parameters for this magnetic field model. But if we want to know about magnetic fields, we also need to know about the other components of the galaxy, about thermal electrons, cosmic rays, dust. And that then we can simulate a Milky Way galaxy, simulate data, and compare that with all kinds of different data sets using this software. And because it's Bayesian, we can also include theoretical knowledge, any theoretical knowledge that we might have on these magnetic fields. For instance, constraints from cosmic ray distributions or constraints from dynamo theory, and that together. So it's a modular software suite, so you can input all kinds of different models. You can input all kinds of different data, and the goal is that can then compare these different models, make new models, and that we will be able to find something like the standard model for the galactic magnetic field, which doesn't mean that it's a perfect model, of course, but it would mean that this is the model that we can agree to, that is the best model available at this point. So now very quickly, a side path that Imagine is not only a software suite, but it's also a growing into something like an open science consortium. We have now a couple of dozen people together. I think by now there are 80 or 90 people on the mailing list who are in some way interested in galactic magnetic fields and interested in interacting with each other on this. We have, well, in principle, we have every 3 months a seminar, although this has been tough to keep to in the last Corona year. We try to hold workshops, and then we have this mailing list that doesn't have a lot of traffic, but some announcements and things. So this was the last meeting that was organized, but as you can see in the date, by the date that was canceled. But now we have a new meeting scheduled in the Lawrence Center called Modeling the Galactic Magnetic Field, which will probably be a hybrid meeting, well, in person for a few people, if possible, at that time, but then online for many of the people around the world who are not yet able to travel. And so if you're interested, please check out the webpage and put your name on the mailing list if you want to be involved or up to date and in whatever way. Okay, so back to the software, and in particular the data, because the rest of the talk I'd like to spend on 2 data sets in particular, which is Faraday rotation, giving rotation measures, and starlight polarization. So let me discuss both in turn, and then also tell you what kind of results you can get, so what the advantages are of both of these methods, and a little bit of what our group is doing with these. So first, rotation measures. There are basically two ways to measure Faraday rotation, and the first way is what we call the rotation measure grid. So your rotation measure is measured from polarization angle change with frequency, and a rotation measure is proportional to your parallel, to the magnetic field component, which is parallel to the line of sight, which is what we're after. But it's also proportional to the thermal electron density, and that integrated over the whole line of sight between the source of the polarized emission and the observer. So you can use basically any source for this polarized emission, but if you use extragalactic sources at the typical resolutions that we observe at, which is mostly point sources, so they're radio galaxies, quasars, things like that. But all we're interested in is that they're slightly linearly polarized, and this linear polarization is Faraday rotated when it travels through the Milky Way, and most of its Faraday rotation is due to the Milky Way. And so probes the magnetic field in the Milky Way. So this picture you see here by Sebastian Hutschenreuter is the whole sky, and it has about 50,000 dots, and each dot is an extragalactic source of which the rotation measure has been measured. And you see that goes from negative to positive. In general, the rotation measures are much higher in the plane, right, because there the path lengths are higher and electron density is higher. Possibly magnetic field, but maybe not so much. And so from all these sources, you can find information on the galactic magnetic fields. But then another source of this radiation is the synchrotron radiation in the Milky Way itself. And so in the Milky Way, this synchrotron radiation is a diffuse continuum background, which is a parallel in frequency. And in the gas that emits this emits the synchrotron emission, there's also Faraday rotation in the same medium going on. And then you cannot define a rotation measure anymore, but you have to resort to a more complex method. And that complex method we call Faraday tomography. And I'll try to explain. And so the Faraday tomography depends on Faraday depth, which is phi. And you see that the definition is very, very similar to the definition of rotation measure, except that the integration is not over the whole line of sight from the source to the observer, but is over different parts, little parts of the line of sight. So your Faraday depth is defined as a function of your path length, which makes it basically possible to probe little parts of Faraday rotation along the line of sight. And how that is possible is described here in the below. Then if you have these little parts of Faraday rotation along the line of sight, you can make this into a spectrum, which we call a Faraday spectrum here, which is f of phi. And the spectrum tells you how much polarized intensity there is at each Faraday depth, so at each amount of Faraday rotation. And so if you take this spectrum that tells you how much emission there is at a certain Faraday depth, and you integrate that over all the different Faraday depths possible with the correct Faraday rotation here in the exponent, then what you end up with is basically your observed polarization. So P is the observed complex polarization as a function of wavelength. And this W is a window function to take care of the imperfect frequency coverage. But then basically, if you add up all the different Faraday depth components, you should see, well, basically this complex polarization. But this is, you can Fourier transform, you can invert this equation to the equation that is below there. And so then you can actually determine the Faraday spectrum, or, well, an approximate reconstruction of this Faraday spectrum from the complex polarization. If you measure a complex polarization at very many lambda squareds, and you integrate over that lambda squared, over the wavelength squared, you end up with a Faraday spectrum. So you end up with Faraday depths as a function of line of sight. Now you can immediately see there are a few problems with this equation, that we have to integrate wavelength squared from minus infinity to plus infinity. And of course, the problem is that lambda squared, negative lambda squareds do not exist. So that's a fairly fundamental problem. And then there's also the practical problem that even the positive lambda squared, so the frequency channels we have in our observations are very limited, and they certainly don't go to plus infinity. And so this problem is very similar to radio interferometry, which has the same kind of Fourier pair in the UV plane, in the imagery plane, and the same imperfections that a non-perfect UV coverage gives you artifacts in the radio images. And here it's exactly the same, that if you have an imperfect, so a smaller than infinite number of frequency channels, that'll give you artifacts in the Faraday depths. And so on the one hand, this is a very powerful method, because what used to be just one rotation measure is now a whole spectrum of Faraday depth components. But on the other hand, we are still trying to learn what these artifacts actually tell us, and well, what these artifacts actually are, and how we can remove them from the data. So this is the math. If you show exactly the same in pictures, it is something like this. This is a nice, simple picture by Marta Alves. And if you have your radio telescope here, and I look at a certain line of sight, there here in this left-hand situation, there are a couple of clouds. Here, the light gray clouds are clouds that Faraday rotate due to a magnetic field in the red arrow that is in this cloud. And the blue clouds are synchrotron emitting clouds. And so what you see with your radio telescope is two sources of synchrotron emission along this line of sight, and they're both Faraday rotated by some amount. And so if you plot the Faraday depth phi here as a function of this path length, z, you see that your Faraday depth starts to increase at the moment where you hit the first cloud. This increases because the parallel magnetic field component is towards you, and towards the observer means a positive rotation measure and a positive Faraday depth. So this Faraday depth increases and increases until the edge of the cloud, and then it stays constant through the synchrotron emitting cloud. And then here, this other Faraday rotating cloud has a magnetic field away from us, so it has a negative Faraday depth. And so the total negative depth, the total Faraday depth decreases again to some value phi 2. So the Faraday spectrum that you end up with then is you get two sources, two bumps of polarized intensity, one from the one synchrotron cloud and one from the other synchrotron cloud, but they have different Faraday depths. So the nearest cloud has this Faraday depth phi 1, so you see a peak at phi 1, and the further cloud has another peak, but at the lower phi 2. And now this is a fairly simple situation. In the real situation, the Milky Way will often have these clouds mixed, so Faraday rotation and synchrotron emission mixed. And what you get then, you see in the right-hand plot, where here there's this one cloud that is both emitting and rotating. And you'll see the same Faraday depth structure as a function of the line of sight, first increasing with the first cloud and then decreasing with the second cloud. But now things are different for this synchrotron emitting cloud, because the emission that comes from the beginning of this cloud, from the near end of this cloud, will have a different Faraday rotation than the emission from the backside of the cloud. And this ends up in the spectrum as a broad component, which we call a Faraday thick component, so that this one cloud has many different Faraday depth values, and not just one, as in the one, as in the first example. And so these are very simplified examples. What it looks like in reality is something like this. And this I find an amazing picture. I'll explain to you what it is, but first let me point out the scale to you. So this is in galactic longitude. This is almost all of the northern sky here, and this is 30 or 40 degrees in latitude. So this is a huge part of the northern sky. This is observed with LOFAR by Anna Erceg in Zagreb, Croatia. And the different colors that you see are different slices of Faraday depth, so different Faraday rotation components. And then the intensity of the color is the amount of polarized intensity from this. So you see this very bright arc here, and this thing is actually loop 3. It's one of the galactic loops that you can see in the radio sky. They're thought to be old supernova remnants, but you can see this in polarized intensity very well. And now for the first time, we have a handle on the details of magnetic fields across this loop. And these are, I think, a little bit more complex than Anna would have wanted, but you'll see here, you see a gradient, the different colors, you see a gradient in Faraday depth across the loop, which might be a gradient in magnetic field strength. It might also be a gradient in magnetic field direction. But you also see some gradient-like structures and small-scale structures across the loop in very different ways. So this makes the complexity bigger, but it gives us a handle on what different Faraday depth components along the line of sight can be. But then, with only this method, we do know that there are different Faraday depth components along the line of sight, but we don't know where they are. We don't have any distance information. We don't know their order, which is close and which is far away. And so if we want to really pinpoint where these Faraday rotation components come from, we need some other way to give them distance estimates. We need a correlation with a different ISM component or with a different astronomical component to be able to pinpoint where they are exactly. And one excellent way to do this is by looking at the polarization of stars. Because most stars are unpolarized intrinsically, but then they can attain a little linear polarization by propagating along the line of sight in the interstellar medium. There's a nice graphic here to the left where you see a star that is intrinsically unpolarized, But if the light from this star travels through a dusty medium, here these red ellipses are dust grains, in a magnetic field, these dust grains will partially align with the magnetic fields, and they'll cause more absorption in the one polarization direction than in the other polarization direction, effectively giving a slight linear polarization to this stellar light. And here to the right, you see the most famous catalog, or a visualization of the most famous catalog of these starlight polarization values from Carl Heiles in 2000. And so you see, this is the whole sky, and along the galactic plane, you see that every stripe representing linear polarization from a star, all of these stripes are pretty much correlated with each other, indicating that it's not intrinsic linear polarization of the star, but you're really looking at these larger scale interstellar polarization here. Here you can also decipher one of these galactic loops. This is the North Polar Spur there. So this is a very exciting method because, of course, from all these stars, especially now with Gaia, we can get distances to all these stars. And so if this linear polarization due to the magnetic field in the interstellar medium, if that correlates with the Faraday depth structures that we see, then we can actually define a distance, assign a distance to these structures. And so a number of people have been looking into these correlations between different magnetic field tracers in the Milky Way lately. And there are some nice examples here. This is one by Susan Clark, where she showed that the magnetic field orientation from Planck polarization, which you see here in the color, and here the lines are again a visualization of Planck magnetic field orientation. And this correlates with the little white lines that are magnetic field orientations from starlight polarization. Now, both of these methods probe the magnetic field in the dust, right? They need dust for their measurements. And so it's not very surprising that both of these correlate. And another correlation she finds is the correlation of this same starlight polarization, but then with a neutral hydrogen, with H1. And again, this is not very surprising because neutral hydrogen and dust are very well correlated in the sky, especially here in the high latitude sky. So again, it's not surprising that the neutral hydrogen is also well connected with dust and correlated with the starlight polarization. But then here's one thing that did surprise us more is that this. Sorry, the title is wrong. I should say dust polarization with Faraday depth filaments. I see this only now. That what you see here is a high latitude field in the sky, and these colors are again different Faraday depth components. And the gray lines you see through it is dust polarization from Planck. And you see that the edges of the colors here and here, they correlate very well, and even here, they correlate very well with the magnetic field orientations of Planck. So this means that these different Faraday depth structures, they are correlated in some way with the dust. And this Faraday rotation, as I've said before, this depends, it has nothing to do with dust intrinsically, but it depends on ionized gas. So, and the Planck submillimeter polarization depends on dust. And so this one field is proof that there is, at least in this field in the sky, is a very tight correlation between the ionized gas and the dust here, because you do see the same kind of magnetic field structures in both. I should say that this is not the case for all fields, and that in this paper they looked at some other fields that did not have this correlation, but this field does, which is very interesting. Because then that might mean that this starlight polarization is also correlated. And if it does, then we have these distances from Gaia. And indeed, we tried this in a couple of fields. This is one example of Luca Turric that looked at this field. Here's polarized intensity, Faraday depth components. And indeed, he saw two different, basically, groups of starlight polarization. That I see I go way too slow. So I'll go through this very quickly, that these two stars, they seem to have related angles, but they're at very different distances. And these angles, the polarization angles of these two groups of stars are correlated with the orientation angles of the Faraday depth components, which can, makes us that we can tell from the stars that there has to be one nearby Faraday depth component and one further Faraday depth component. And let me go quickly to the biggest starlight polarization results that we're now analyzing with Antonio Mario and Claudia and Reinaldo and other collaborators. And this is at this moment from the Interstellar Polarization Survey. This is a survey that Antonio Mario and collaborators had done many years ago, and that we're now ready to analyze through. The data is processed, and this is my PhD student, José Versteeg, is now looking at this data in detail. And so the Interstellar Polarization Survey, you see here in all these little circles. These are very focused observations of optical polarimetry in fields. Here, this is an example of about 0.3 by 0.3 degrees. And they have a stellar density of, well, a few hundred to more than 1,000 stars per field. And that for a few dozen of these little fields in the sky. So what José finds in statistics of these stars in these fields is the following: is a degree of polarization of a few degrees, which is what we'd expect. The polarization angle that peaks around 90, and this 90 is approximately the parallel to the galactic plane, which is what we need. And the distances are about up to 3 or 4 kiloparsecs. And these are distances that are basically, this is based on Gaia parallaxes. And so from this polarization angle, for instance, this is a very direct measure of magnetic fields, of the orientation of magnetic fields. So from that, we can get the average orientation of the plane of sky magnetic fields. But we can also, from the dispersion of polarization angles, and using the DCF method, the Davis, Chandrasekhar, or Fermi method, we can find an estimate of the field strength. I'll get back to these both things. But then the degree of polarization is more complex, because it doesn't only depend on magnetic field, it also depends on dust parameters. And so from that, we can get to the dust properties. It has information on the dust properties, but also a little bit on the tangling and the orientation of the magnetic field. And how to get that out is exactly what we're doing, what we're trying to do right now. And I'll quickly, as a last thing, I'll discuss each of these arrows and each of these methods in one slide of what we're trying to do here. So first, the average orientation of the plane of sky magnetic field is what you see here. This is an all-sky image of Planck dust polarization. And again, these lines are magnetic field orientation. And all these black dots are the points, the fields of our survey. And these lines are the average magnetic field direction integrated along the line of sight in our field. And you see many of these do agree with the Planck magnetic fields. And what is conspicuous is that almost none of these average magnetic field directions are really in the galactic plane. Right? Naively, in a simple model, you would expect the large-scale magnetic field to lie in the galactic plane, but it doesn't. And it also doesn't for instance, in a different survey, the Galactic Plane Infrared Polarization Survey, where Dan Clemens and collaborators find exactly the same effect, that the average magnetic field is not 90 degrees, but in their field is actually 76 degrees. And so this points to some kind of intermediate scale structure that complicates our models. The second point was to get the field strength from the angle dispersion. And how you get that is here through the DCF method that I mentioned, and that is basically this this equation, and that you can understand that you get the magnetic field strength from the ratio of the gas velocity dispersion, the gas velocity dispersion, and the polarization angle, the dispersion, which means that if the gas is very turbulent, so the dispersion is very high here, but the dispersion and polarization angles is still nevertheless very low, that means that you need to have a very strong magnetic field to keep these these polarization angles from wobbling, which means that here your B is very high. However, if your angle dispersion is also very high, then that indicates that the magnetic field that's causing that is much smaller. And so we tried this with a bachelor student at Radboud University to find the velocities from the H1 spectra, find the polarization angle dispersions from the IPS, so from the Interstellar Polarization Survey, and derive magnetic field strengths for that. Now, don't believe these magnetic field strengths, because there are still some problems with the method, but in principle, we can try to do this. And so this is something that we want to look back into, trying to get better velocity dispersion measures than we had. And we can also now correct for, well, there is a correction factor for this equation that does not only allow alphanic turbulence like this equation does, but also MHD turbulence. So this is what we're trying. And then lastly, another intriguing aspect is the polarization, so the polarization fraction. And this is measured, we measure this in terms of polarization efficiency, which is the polarized intensity over the reddening. So basically is how much polarization there is per unit extinction. This is work by Jennifer Angarita, who is another PhD student in our group. And she has looked into and compared the IPS field with what we call the classical limits to that. This is Surkowski, did some seminal work in the 70s and found that this polarization efficiency is always smaller than about 9% per magnitude. Now, the Planck collaboration looked at high polarization fields and found that some of these fields actually were surpassing the Surkowski limit, and so had a higher polarization efficiency. And a higher polarization efficiency probably has to do with turbulent fields, causing more or less depolarization, or with the direction of the large-scale magnetic field. And so Jennifer is trying to figure that out for the Interstellar Polarization Survey, and this is one of the fields that she analyzed. Here, every dot is a star, and this is the polarization as a function of the reddening. And so these two classical laws are given here by the orange and the blue lines, and you see that in this field, but also in some other fields, the polarization efficiency is even higher. If you plot all of these upper limits, all of these polarization efficiencies, and this is what Jennifer gets, where here the red one is this upper limit from this field, which is the highest, but all these different lines are upper limits from different fields that we get. So some of these are even lower than the Surkowski limit, some of them are higher. And here are two more examples of these fields. And so we're currently trying to figure out how we can get this information of the magnetic fields, directions, turbulent magnetic fields that has to be in the variation of all these polarization efficiencies, how we can get them out. And now, after a very brief look at the future, I'd like to summarize, and this is the future, our future in this endeavor is hopefully the South Pole Survey. Now, I can't imagine that you haven't heard at the University of Sao Paulo Astronomy Department of the South Pole Survey, because here Antonio Mario is the PI of it, Claudia Rodriguez is an important puller of this, if that's a word, and a driver of this survey. And this is after the few dozens of fields that we have now. We would like to be able to image the whole southern sky in starlight polarization, in optical linear starlight polarization, to be able to get a complete view, a 3D complete view of the magnetic fields in the Milky Way. Okay, so with that, I'd like to summarize that I briefly talked about modeling first, that we do have more and more advanced models for the GMF, for the galactic magnetic field, and we're trying to put these models, or to actually parameterize these models and find best fit parameters using our Imagine software. And really, the 3D data sets of observations are really the future, because that's the only way in which you can really probe this field in detail. And Faraday tomography is one option, but starlight polarization, especially the South Pole survey, are also very promising future avenues for this endeavor. Thank you.
Thank you, Marijke. Extremely rich in physics, the presentation in astrophysics. Let's go to the questions. So the first is Juan. Please, Juan, go ahead.
Hi, thank you for the talk. I have a very quick question. So in your technique for tracing magnetic fields based on polarization from starlight, what is the most appropriate type of star for doing this, for instance, massive stars or low mass stars? Do you take into account the intrinsic magnetic, stellar magnetic field?
Yes. Okay, that's a good question. It's only very few of these stars are intrinsically magnetized, or well, it's actually the circumstellar matter that makes this the polarization. So most of the stars that we look at are intrinsically unpolarized, and all the polarization we measure is due to the interstellar magnetic field. And this is what we want, of course. We want to look at the intrinsically unpolarized stars. And the ones that are intrinsically polarized are the ones that have a lot of circumstellar matter around them. So are most of the massive stars, evolved stars. And so those are the stars, but luckily there are only few, relatively few of them. Those are the stars that we suspect have intrinsic polarization. But so we are trying to figure that out in more detail now. But if you look at these fields, then most of these polarization directions are very much aligned, or they vary a little bit. But once in a while, you have a star that has a polarization completely in the different direction. And of course, that's a candidate to start looking for intrinsic polarization. But for most of them, we're pretty sure that the polarization is interstellar, which is exactly what we want.
Oh, thank you very much.
Now, Maria, please go ahead.
Yeah, oh, sorry. Okay, thank you very much for your talk. It was very clear. I have many questions, but I will just ask one question, and then if we have more time, I will ask more questions. I am curious about, you mentioned some data input that you use is the synchrotron emission, and I was wondering what are the main sources of this synchrotron emission, if they are galactic ones or extragalactic?
Yes. Actually both. So the main source is, well, one main source is the galaxy. So it's this diffuse continuum maps of the whole galaxy, the Haslam map, and at higher frequencies, at different frequencies, you can give these maps as input in these galactic magnetic field models. This is actually one of the traces that has already been used a lot in the past decade to make these models. You can also look at synchrotron emission from extragalactic sources, but that synchrotron emission then is, well, it's intrinsic to the source, so it doesn't have to do anything to do with the galactic magnetic field unless it is Faraday rotated through the Milky Way. So then you look at the Faraday rotation of that synchrotron emission, and that again gives you information on the Milky Way.
So when you are doing this Faraday tomography, you are using the extragalactic synchrotron emission?
No, sorry, I may have misunderstood you. For the Faraday tomography, we're using the galactic emission. So we're using the diffuse synchrotron emission.
Okay.
That is at different distances along the line of sight. There's always this galactic diffuse emission.
Okay. Thank you.
Well, I also have a couple of questions. Let me ask just one, and if I have more time. In the beginning of the talk, I think you showed a comparison showing the deflections of the ultra-high for ultra high energy cosmic rays for different models of magnetic fields. I'm curious because there is one region in the galaxy where they seem to agree better, and I would like to know if this is because this region is better constrained, this right side in the middle, it's better constrained, the magnetic field, or is there some special reason?
I'm not sure. What I suspect is that at that point, the orientation of the large-scale magnetic field is such that the deflections of these cosmic rays are the smallest. So I think it's purely an orientation issue.
It's more related to intensity. Okay.
Yes, and the asymmetries then are because of these, because the spiral arms and vertical components are not symmetric.
Right.
From seeing from the place where we are in the galaxy.
Thank you. Antonio, please.
Yeah, thanks, Marijke, for a great talk. I like the way you taught the Faraday rotation, because I never saw it really in detail. So it was good to hear you and understand it. Especially, I suspect that SKA is doing that, right? Something like that. Yeah, right.
Yes.
So when you I have several questions as well or comments. I'll just keep myself to two. So if there is time. So you're measuring that's a complex polarization, right? So that's an amplitude, which I suspect would be a fraction of polarization or something, and then a phase. So that phase is something. Is that so? You measure that phase. I mean, let's say you compare two frequencies or two wavelengths. Is that what it is? You just need the relative phase. Is that what it is in practice? Is that I understand it correctly? Yeah.
If I understand you correctly, you understand it correctly. That doesn't tell you much. This phase, so the phase is a polarization angle.
Right.
And the exponent here that you see in the, you probably don't see my cursor anymore, but the exponent that you see in the Fourier equation there is the Faraday rotation of this angle.
Okay.
And so every different Faraday component has a certain intensity, right? This intensity in the spectrum that you talked about, but it's also Faraday rotated by a certain angle, and that is frequency dependent. And so if you have enough frequencies, you can actually disentangle all these different rotations, and then you can get to all these different Faraday depths.
Okay, got it. Okay, yeah, thanks. Okay, got it. Thank you. And the other question about radio galaxies, which you have worked with. I was watching a talk the other day by, I forget the person, but anyway. People have been using for external galaxies, like M82 or Centaurus A. They look at the let's say with submillimeter, like instruments like SOFIA, you can get like the whole galaxy, but a very relatively poor resolution, right? And then you get the emission from dust, and then you measure the overall structure of the magnetic field. And in some sections of a galaxy, they use ALMA. Then it's a very high resolution, but of course, it's a very small section. So I suspect you could still use line transitions to get the random component of the field from equipartition. But in terms of estimating the more uniform, the more general line of sky projected magnetic field, they don't have enough resolution to use, a structure function maybe or something like that. Could they? I guess they could use radio observations. Does that make sense to you to use estimate B? I mean, the overall B from radio. Does that make sense to you? Since they have this resolution, inability, right?
Yeah. No, I think that definitely makes sense. Actually, if you use the lower frequency radio synchrotron emission for this, then and you have to assume equipetition or well, I lost the word, equipetition for of cosmic rays and magnetic fields, then you can indeed estimate a field strength. And this is what people like Rainer Beck have been doing for a long time. I think what now these higher frequency instruments can really add, is, as you say, is resolution and smaller scale structure. Although still in any external galaxy, you have the problem that you're looking right through the galaxy, right, in dust emission, as well, the same problem as we have in the Milky Way. But yeah, I think the interesting, the point where we are right now is that we can actually start combining these low frequency synchrotron emission and then with the dust polarization. And so all these components give you different components of magnetic fields or magnetic fields in different gas components, different gas phases. And so we're now, I think, at the point that we can start to combine these in the Milky Way, but also in external galaxies.
All right. Okay, thank you.
No, Walter, please go ahead.
I have a question also about external galaxies. Is it possible to relate these results for the Milky Way to galaxies such as M51, where you have a clear view of the magnetic field structure along the spiral arms?
Yes. Yes, that's a very interesting question. Of course, it would be great to look at external galaxies and to try to predict what that might mean for the Milky Way. As far as I know, what we see in different, face-on or edge-on external galaxies is so different that it's hard to predict for the Milky Way. What we see, for instance, in M51, right, which is a Milky Way-like galaxy, we do see these magnetic fields following spiral arms. So this is one of the arguments why our heuristic models all have these magnetic fields following spiral arms. But you do see small-scale structure there as well, which is well, okay, that is, which we know is in the Milky Way, and we cannot probe very well in the Milky Way. So I think to a certain extent, you're definitely right that there is a lot of communication, I think, and interplay between Milky Way, magnetic fields, scientists, and people working on external galaxies. But on the other hand, every galaxy seems to be different as well.
So before I make my second question, I'd like to pass one question from YouTube. So we have a audience also from people who are not researchers in the field, and Antonio Sanchez, sorry, he's asking for you to make some comments, if you can make some general comments about the applications and motivations to the study of the structure of the galactic magnetic fields.
Sure. Now there are two ways to answer this, I think. Is what is the use and application of these studies to the field, to the fundamental science? And of course, a much broader is why would you need something like this in society? And I'm not sure which of the two, can you derive from the question, which of the two is meant? I don't know.
Sorry, it's maybe you can comment the motivations inside the astronomy, maybe for other fields in astronomy.
Okay. Yes. So this is basically, well, the magnetic field behaves very differently in space as we're used to here on Earth. because in space, basically everything, almost everything is ionized. The gas is ionized, the interstellar gas, stars are ionized. And that reacts much stronger to magnetic fields as the solid and the neutral materials that we're used to here on Earth. And so these magnetic fields do have a very direct influence on basically every component in the Milky Way and broader in the universe. And because they're dynamically important, which means that the energy is contained in these fields is approximately equal to the energy contained in gas, approximately equal to the energy contained in cosmic rays. That means that if you want to study the gas, you need to know about the magnetic field and the feedback of the magnetic field of that. If you want to study how stars form, you will need to take magnetic fields into account. And so for many of the studies of other aspects of the Milky Way, you will need to know to some amount of detail what the magnetic field behaves, what it looks like, and how it behaves. But also, I think a second important point is that this magnetic field is also, it's in the way of extragalactic observations, right? For instance, ultra-high energy cosmic rays, but also if you want to look at the polarization in the cosmic microwave background, you have this pesky Milky Way in the way, which has a lot of polarization due to its magnetic field, and that is something you want to get rid of and subtract. And so a good enough model or a good enough description of the galactic magnetic field is also important for extragalactic science, extragalactic fields, where people want to look beyond the Milky Way and just subtract this annoying magnetic field.
Thank you a lot, Marijke, for the comment. And if you allow me to make a short last question about the Faraday tomography, is it possible to make this study only in the plane, or somehow is it easier to analyze data out of the plane? And I don't have any intuition what's the best target for.
Yes, it's a good question. And the answer is that depends on your frequencies. If you look at, for instance, this field of IAG, this is LOFAR, so this is very low frequency. And at these very low frequencies, the Faraday rotation is very high. And that means that you decorrelate very quickly. There's a lot of depolarization. And the practical consequence of that is that everything you see here in polarized emission is really nearby. It's in the nearest few hundred parsecs. And after that, it's depolarized. So this is out of the plane. If you would look into the plane, everything is immediately depolarized. And so this at these very low frequencies, it's best to look out of the plane. However, if you go to higher and higher frequencies, there is less Faraday rotation, which means that you get less depolarization, which also means that you have a lower resolution in Faraday depth. So which means that you cannot see the very small scale structure in Faraday depth, but it's more smeared out. And so, for instance, if you go to common radio frequencies of 1, 2, or 3 gigahertz, something like that, there it is better to look in the plane, because then you can detect the higher Faraday rotations that you expect in the plane, but then you cannot see as much detail as you would with LOFAR at the high latitudes. So it's really, you can pick and choose different frequency coverages to try to get different parts of the Milky Way, so nearby stuff in the plane or out of the plane.
Thank you. I think Antonio Mario has a last question.
Yeah, thanks, Reinaldo. It's just a brief comment, and I think Marijke could do that as well. I mean, once Marijke mentioned South Pole, and once we get things going, or we know at precisely more details, in more detail how we are going with the survey, we will be announcing, making that public, and people who like to collaborate with us with the survey will be welcome to do that and encouraged to do that. Yeah. So we'll have more news, right, Marijke, in a short period of time, hopefully.
Thank you for that very useful addition. Yes.
Okay. I would like to thank you again, Marijke, for being here and sharing your knowledge, your research with us. Thanks a lot for the talk.
Thank you all for listening and for the many questions. It was a lot of fun.
Many thanks everyone who is present following this talk. Thank you everyone for participating. We can stop the transmission now, Alexandre. Podemos desligar agora a transmissão, Alexandre.